Hello, all welcome back to the hypothesis testing session. So, in the last class, I have discussed about the chi-square test, which was basically for the single population variance test. I mean, so in this session, I will be discussing about the hypothesis testing for two population variants, and that is generally known as F test because we use the help of F distribution to make the decision about uh, the rejection or acceptance of the null hypothesis or the rejection or the acceptance of the null hypothesis under this test. So F distribution, like the chi-square distribution, it is also a family of distribution depending on the degrees of freedom. Okay, you have the distribution with a different shape. So that's the reason it is called a family of distribution. And the same way, chi-square random variable was assumed only positive values. The F distribution also, the F random variable also assumes only positive values. So that's the reason you have 0 at the left end of the distribution. So you have different shape of uh, F distribution with respect to two degrees of freedom. Okay, since we are dealing with two population variants, so you have different distribution with respect to different degrees of freedom. Okay, and as you can see, the difference from the chi-square distribution uh, to this F distribution is basically the peakedness. As you can see, it is more peaked than the chi-square distribution in the left, right? And this distribution also tends to normal distribution when the degrees of freedom increases. As you can see, this the center one, the brown colored distribution, almost I mean in some extent there is a tendency to tend it to the normal distribution. That's because of high degrees of freedom. But still, this is not, I mean, not replicating the normal distribution. Uh, but when you increase the degrees of freedom, you will see even the F distribution tends to the normal distribution. I mean, it can be more than 30. When you increase, when it goes more than 30, you will see it follows almost a similar shape of uh, normal distribution. So that is all about the F distribution. Then coming to the usage of F test. Okay, F test is based on the F distribution. So the usage of F test are like this. I mean, these are some examples, but there are different. I mean, different places it is used, and across. I mean, disciplines it is used. So two examples are like this. It is used to test the consistency in the performance of a product. Okay, suppose you want to test whether the output given by a specific product is different from, uh, I mean, a similar product which is produced by a different company. So in that case, you can use F test. And coming to the stock market, as I discussed in the chi-square distribution, here also one can use. I mean, here also you can analyze the variance and compare the variance of two stocks using this F test. Especially you as an investor will be interested to invest in a stock which provide less variance, right, which is the variance is less. So I mean, this is one test you can use to to check whether sorry, which stock provide less variance. Now coming to the null and alternative hypothesis specification, null hypothesis is always specified as sigma 1 square equal to sigma 2 square. So sigma 1 square stand for the variance of first population, and sigma 2 square stand for the variance of second population. But you have three different forms of alternative hypothesis specification depending on the whether you are testing depending on whether it is a two-tail or a one-tail test. You have three different forms of alternative hypothesis specification. For right tail test, your alternative hypothesis will look like this: sigma 1 square greater than sigma 2 square. For left or lower tail test, it will look like sigma 1 square less than sigma 2 square. And for two tail test, you can specify your alternative hypothesis as sigma 1 square not equal to sigma 2 square. And coming to the formula to calculate test statistics, this is a relatively simple formula. I mean, if the variance of the sample are directly given, then you can use this formula like S1 square divided by S2 square, where S1 square stand for the variance of the first sample and S2 squares stand for the variance of the second sample. So S1 square is associated with the numerator degrees of freedom, that is n1 minus 1. Okay, so both these variants are are associated with a specific degrees of freedom. S1 square, since it is in the numerator, the degrees of freedom associated with this variance is known as the numerator degrees of freedom, that is n1 minus 1, and the degrees of freedom associated with the denominator variance is called the denominator degrees of freedom, that can be specified as n2 minus 1. So n1 is nothing but the sample of the first sample size of the first sample, and the sample size of the second sample is n2. So you can calculate this ratio, and that will provide you the test statistics. So once you have the test statistics, next step is to compare it with the table value, right? So the table value is calculated or observed or obtained based on two informations. One is, of course, the degrees of freedom, but here you have two degrees of freedom: the numerator degrees of freedom and the denominator degrees of freedom, right? And the other information you require to obtain uh, the critical value is level of significance. So when you go on finding the critical value using the table, the one thing that you should note here is, for a right tail test, it is okay. You can directly go by the given alpha. That is nothing but the level of significance. For example, if the alpha is given as 0.05, then you can directly go to the table and look for that specific area, right? 0.05, and you can look for the corresponding, so you can look for the degrees of freedom, and you can look for the intersecting value, okay, for this alpha as well as for these 2 degrees of freedom. That will be your critical value, right? But when it comes to a left or lower tail test, so when you look for the value, first you need to minus the given alpha, that is 0.05, for example. Then you will get 1 minus alpha as 0.95, right? So you need to look for the critical value in the table. uh, I mean, when you look for the left or lower tail test, your critical value should be corresponding to the 1 minus alpha level of significance and these 2 degrees of freedom. Okay. And again, when it comes to two tail test, uh, of course, your right tail will be alpha by 2. You need to divide your alpha with 2. In your case, if it is 0.05, your right tail critical value is obtained by dividing your alpha with 2. And for example, if you divide 0.05 by 2, you will get 0.025. So you should look for 0 point, the value corresponding to the test statistic, sorry, the table value corresponding to 0.025 for right tail. And coming to the left tail, you should minus alpha by 2 from 1. Okay, you should minus alpha by 2 from 1 to obtain your critical value for the left tail in the case of two tail test. Okay, and this is applicable to the chi-square test also. Remember, this is applicable to the chi-square test also. Okay, and this is the graphical representation of your one tail and two tail critical values. And coming to the, yeah, I have given the what this is an example for, this is just one portion of you know uh, f table value, because you have, this is a big table. Okay, this is a big table. I just took just one portion, and this stand for, as you can see, the p here stand for the probability of rejecting none, that is nothing but alpha, right? The probability of committing the type 1 error, that is your alpha, that is nothing but the level of significance. And this entire table is only for 0.1 level of significance. And you have uh, in the first row here, the top row here is the numerator degrees of freedom. Since you have 2 degrees of freedom for F test, you need to go by looking for the degrees of the numerator degrees of freedom and the denominator degrees of freedom. Okay, so you look for the numerator degrees of freedom and look for the denominator degrees of freedom, and also take into account of the level of significance which you are looking for. So confirm that first. And this page actually stand only for 0.1 degrees of freedom, sorry, level of significance. But you have different such tables for different level of significance, especially for the major one, 0.1, 0.5 and 0.05, 0.025, 0.001, 0.95, 0.99. So these are the major level of significance. So you need to go by the level of significance which you have been asked to test for, right? So that is all about today's session. It was on F test, and that too for two population variance. So we are basically testing the difference in the two population variance is statistically significant or not under F distribution, right? So hope you understood what we have discussed so far. So I'm giving you an example. I mean, basically it is an exercise. So I want you to try this. This is an example or a question on the F test. So see, these people basically want to know uh, whether there is any statistically significant difference between the variance of two devices uh, which is used to test the pressure, right? Blood pressure. So uh, you need to test at 5% the level of significance whether the data provides sufficient evidence to conclude that manufacturer's claim is true. So what was manufacturer claim? The manufacturer says that the device that they produce is more consistent than that produced by a leading competitor. Okay, so you have manufacturer uh, test result here. The blood pressure result here, uh, and which was done on one object, and this is on the competitor device output. Okay, so do it and let me know the result, and of course this will have some impact on your CP, so take it seriously, uh, try to do it, and you can uh, mail me the result. So that is for today. So I will come up with uh, other videos on the remaining topics, you know, once in a while. Once in a 2 days or once in a 3 days. Okay, so go through these videos thoroughly, and if you have any questions, please post in the WhatsApp, or you can of course always shoot a mail to me. So thank you. Bye.